Final review for AP Physics C, electric circuits. So electric circuits, we know the VIRP chart, and VIRP talks about the four key words in this: voltage, current, resistance, power. Voltage is a independent variable in circuitry. It's controlled by the power outlet or by the power source, whether that be one of the electrical boxes we've used in lab, or if it's a battery. The 9-volt battery, for example, is going to give you 9 volts. That's it. The 120-volt wall outlet is going to give you 120 volts. It doesn't matter how much stuff is in the circuit. That's your voltage. Voltage is an independent. The other one that is usually an independent is resistance. Resistance is a measure of the impedance in the circuit, and it can be whether it's a carbon film resistor or an appliance or whatever it happens to be. That's typically a resistor. There are non-ohmic resistors, but the majority of things we deal with are ohmic in nature. So resistance, more often than not, I would say 90+% of the time, would be an independent. Now, voltage and resistance as independents create the dependent variable of current. So current is determined by how much push you get from the voltage and how much resistance you get from any resistors within the circuit. Power is the final measure of how much energy is being consumed every second. Don't confuse power with energy. Power is an energy rate, which means it's divided by seconds. Two of the lesser used and known equations, but I do want to point them out, are the resistance of a wire. It equals rho L over A. Rho is the resistivity of the wire given in ohm meters. L is the length of the wire, and A is the cross-sectional area of the wire. The other one is I equals Q over T. I is the current, Q is the charge, and T is time. Those are just two equations I want to point out in case they sneak their way into the exam. You obviously know V equals IR, P equals IV, the resistor for series equation, resistor for parallel equation. Speaking of series and parallel, those are the two primary circuits we deal with, as well as complex circuits. I don't see them giving you just a series and just a parallel. I'm pretty sure it'll be a complex circuit if you get a circuit. In a series circuit, or a portion of a circuit that is series in nature, it means that the current has no choice but to flow through all those resistors along said wire. Whereas in a parallel circuit, the current can split up. Now, an important thing to note is in a series circuit, current does not split up, but voltage is shared. In a parallel circuit, the current does split up, the voltage does not. And then we've introduced capacitors into here. So we have an RC series circuit, such as the one shown in this diagram. In this particular circuit, when it is first powered, the capacitor will act as though it has no resistance. As it gains more and more charge, its resistance will increase more and more and more, causing the current to decrease over time and eventually hit zero. When the current hits zero, we achieve what we call steady state. If after that capacitor is fully charged and the current is zero, we remove the battery and reconnect the wires, the capacitor would discharge itself through the resistor. In a parallel setup, such as the one shown here, at first, all current is going to ignore R2, the 500 ohm resistor. It's instead going to choose to go through the 100 microfarad capacitor. That's because at first the capacitor doesn't have any resistance. Now, as time goes on, the resistance of the capacitor, as it gains more and more charge, is going to increase and increase and increase. Eventually, the resistance along the line with the capacitor will become so high that all current will favor going through R2 as opposed to through the capacitor. Now, if we then, once we have achieved that steady state being when the capacitor no longer has current going through it, so we achieve steady state, we open the switch. And we open the switch, and that results in this half of the circuit essentially being nothing. It's out. It's done. And all we have here is a continuous loop. Why wouldn't the current flow down this wire? Because it gets to the switch and it's broken. Why wouldn't it flow this way? Because it gets to the switch and it's broken. But it can flow in this square over here. So if we opened up the switch, the capacitor would naturally discharge through resistor 2. Last bit I want to talk about is the multimeter. As we go through this, it is important to understand how do we position multimeter. And so I apologize in advance. The video is going to have a little bit of a hiccup. I stopped it and restarted the recording because I needed to have this set up first. So what we see here is it's a circuit, battery, we have a resistor in series, and then these two in parallel. So if I want to measure the voltage across the battery, I have to take my voltmeter and put the two terminals on either side of the battery. If I would like to know what's the voltage drop across this resistor, one probe here, one probe here. Notice that this one said -6. That's fine. That just means that I've had these two terminals backwards. Now it's a +6. But also notice that the resistor is in parallel with the voltmeter. Same thing here if I want to know what about across this resistor. So current can flow through the resistor and go back to the battery, or it can flow through this red wire, go through the meter, go through the black wire on the other side of the resistor, and then make its way to the battery. So when we measure voltage in a circuit, we keep it parallel. So let's go ahead and say goodbye to the voltmeter. Naturally, a voltmeter will technically increase the current of the circuit and decrease the total resistance. It will do it ever so slightly, so we purposefully make voltmeters to be incredibly high resistance so their impact is less. Now an ammeter, unlike the voltmeter, actually just needs to be plugged right into the circuit in series with that resistor. So like I've done here, I got 0.6 amps going through this first resistor in series. I will go ahead and remove it, connect the wires again. Let's see how much current's coming through the battery. Take the meter and I'm plugging it directly into the circuit, making it series. Cut it again, connect, and the last one I'll show you, let's say I wanted to measure, well, what's the current through this section of the circuit. Plug it in, and success. Again, will the ammeter interfere with the circuit? Yes, it's not perfect. The ammeter will ever so slightly increase the total resistance, and as a result, ever so slightly decrease the total current. So we make the resistance of an ammeter incredibly small and as close to zero as possible.